Alright, this is a finite element problem, and we have a beam, and we have a uniformly distributed load on top of it, marked as W, 6,000 Newton meters. We have E and I given. They want us to find the nodal displacements and the slopes at each node at 1, 2, and 3. They want us to find the elemental forces, the elemental moments, global forces, and global moments. So this is a problem where we have a beam which is set up in a way that is a statically indeterminate situation. This problem shouldn't be new to us. If you're taking this class, probably you should have run into this kind of setup in a strength of material class where we solved this with Castigliano's method, or here I wrote it down and I solved it with the principle of superposition. I did this so we can have something to compare to. If you're interested in going through it, pause the video and go through the calculations. In this video, I'm only going to be explaining the method that we are using in finite elements, where we are using all the matrices and such. Alright, let's get started. First, let's find our local stiffness matrices for both of our elements. We have two elements here, 1 and 2. So when we are working with a beam and we want to find deflection and the slope, this is the formula for our local stiffness matrix that we're going to be using. Okay, let's fill it out. Our L for our first element from here to here is going to be 5. So therefore EI over 5 to the third power. The rest we fill it in just like the formula asks. Now, if we think forward and let's see what is the next step that we're going to have to be doing, we know that we're going to have to cancel out the lines and the rows and columns that we will not need, where we're going to have zeros. Now, if we know this ahead of time, it can save us a lot of time. If you can't think ahead and foresee this coming, just fill out the entire formula. It's just gonna take longer, but you will end up in the same place. Now, how can we take this shortcut? If we look up here, we know that our displacements at 1, 2, and 3, the displacement in the y direction, which are our v's, v1, v2, and v3, these will be 0. They do not move in the y direction, therefore it's 0. Our slopes, on the other hand, this is a pin, this is a roller. Both, all three locations will have slopes. Therefore, we cannot cross those out. So here, v1, v2 will be 0. Therefore, I already crossed it out before I even filled it out. So therefore, I'm just focusing on the information that will remain after I cross stuff out. The same thing for our second element. Our length is 4. So therefore, EI over 4 to the third. The matrix filled out, the exact same matrix here. Instead of 5, like we had for the first element, we have 4. That's the only difference. Fill it out. Again, let's take a look. V2 and V3, we know it will be 0. Therefore, I'm already crossing it out before I even filled it out. So I'm just filling out the slope informations. That's all we have. The only thing, remember that K1 is bordered by a node 1 and 2. Therefore, our information in this one gonna belong to 1 and 2. Element 2 is bordered by 2 and 3. Therefore, the information here is 2 and 3. V1, Phi1, V2, Phi2. Down here, V2, Phi2, and V3, Phi3. Let's simplify it. I got rid of all the v's since they are zeros. Only the phi, the slope representatives, are here. Now, another thing that is useful to do is, since we will combine these two into our global stiffness matrix, it's good to try to think ahead and make it in a way where in front of it we have the same thing. Therefore, we can factor it out, and when we get our global stiffness matrix, it will be less ugly. Here I had the 5 and the 4 to the third powers, and I could not factor those out, so I just move them inside the matrix. That's why we have no more division by 5 to the third or division 4 to the third. They went inside here and simplified out, and this is what we have left. Now, these two, let's go ahead and combine into our global stiffness matrix. Now, here it is, the EI, which we factored out from both of them, and the rest of them filled out. This matrix originally should be a 6 by 6 matrix, right? Because we have V1, Phi1, V2, Phi2, V3, and Phi3. Therefore, this would be 6 this way and 6 lines and 6 columns. But we crossed out all the V's, therefore we're only working with the Phi's. Up and down. Transfer the information. Phi1, Phi1, 4/5. Let's find the same location. Phi1, Phi1 goes right here, and follow the rest the same. If you are not clear how to transfer these two into this, I have other videos at the beginning of this playlist where I go into more detail. So please watch those. Here I'm just gonna focus more on the process. After we have this, let's go to our next step where we start working on our F equals KD. Let's look. In this situation, we don't have the forces, we don't have the displacements. So there's a new concept that we're gonna be working in this problem with, and that is called the equivalent forces. So this might be familiar, F equals KD, from previous problems, but we have an F naught, and this means the equivalent global forces. Now what this means is that we are working with a distributed load up here. Now we're gonna convert this distributed load into moments and forces at each node for each element separately, but the equivalent nodal forces will have the same effect on these elements, just like the distributed load had up here. In a way to say, if, let's see, the beam would be alive, if it had this on top of it or this on top of it, it would feel exactly the same thing. And the reason why we are using these is because we can take these from simple tables, like finite element books they have in the back. The tables describe several loading scenarios. You can take these from there. And now that we have these, we are able to go ahead and find our displacements. Okay, let's see how we proceed. Simply take these formulas that you got from the tables and fill them out. WL over 2 for the force, WL squared over 12 for the moment. Fill it out, and this is what we have at node 1. F1, M1, and we have our values. At F3 on this side, the same thing, just like we did here, and you have F3 and M3 calculated. Now for F2 and M2, here it gets a bit more trickier, but not too bad. What we need to pay attention to is that node 2 is shared by both elements. Therefore, our equivalent nodal forces will be added up. So my equivalent nodal force F2 at node 2 will be the value that we get from here plus the value that we get from here, equals 27,000. The moment, let's do this here for element 1, we have this moment going counterclockwise with a value of 12,500. Here we have a moment going clockwise with a value of 8,000. Opposite directions, so the difference between the two will be a counterclockwise moment with 4,500. 12,500 minus 8,000. Simple as that. We can also draw a brand new sketch for ourselves, and we can see this is our beam, and these are F1, F2, F3, and the moment that we just calculated here, our equivalent forces that we replaced our distributed loads with. Now we can go back and start working on the formula that we started earlier. F naught equals K times D. Let's expand this into matrix form. The F naughts, F1, M1, F2, M2, F3, and M3 times our K, the global K that we calculated, times V1, Phi1, V2, Phi2, V3, and Phi3. Now, we thought ahead and we canceled everything out that were zeros, right? So therefore, the only thing we have left is M1, M2, M3 with their corresponding slopes. This here is the global stiffness matrix that we calculated earlier, and there it is. Now plug everything else in that we have, moment 1, moment 2, and moment 3. Now, one thing to pay attention to. All these values, they are just the positive values, the magnitude, so to say, of everything that we see in these sketches. Their direction, the negative or positive, it's shown in the sketch. So therefore we don't write it out here, just like we did in strength of materials. But now, when we come over here and we plug stuff into these formulas, we do not bring the sketches with us. So therefore we need to make sure that our signs come with our values. Like here, M1, we wrote 12,500, but if you look in the sketch, negative 12,500. This is a clockwise rotation. So make sure you don't forget your signs when you bring your numbers from the sketches, from the equivalent nodal forces that you wrote up here, into your matrix setup. Now this here will turn into a 3 equation, 3 unknown situation. We can go ahead and solve it that way, or I just simply like to go ahead and plug it into my calculator and do a RREF, reduced row echelon form, and find my 3 values, which are right here. They are slopes, and the unit for them is radians. Now from here there would be 2 ways to proceed, where we could continue and find our global forces first and then find our elemental forces, or we can take a detour first and find our elemental forces first and then come back and compare them to our global forces, and actually going and doing our elemental forces first will be a little bit beneficial, and we'll see on the end why. So here's the formula that we are working with. Our forces, these are the reactions that we are looking for, right? The one that they asked us to calculate. So the reactions equals K times displacement minus our equivalent forces. Now, the same formula, we're going to write it up and use it in elemental form, where I'm going to start with element 1. So the local forces, the local reactions on element 1 equal the local stiffness matrix for element 1, displacement minus the, and we're gonna use our equivalent nodal forces on element 1. So we're gonna use this one first. Let's go ahead and expand these. F1, Y1, M1, F2, Y2, F2, Y, and M2. So all these belonging to element 1 right here. The same formula that we used, but this one is our local stiffness matrix for element 1, the displacements that we calculated earlier, and minus our equivalent nodal forces just for element 1. Here we don't really have a notation for this, so I'm just writing F naught, M naught, F naught, M naught. Let's go ahead and plug everything in that we know. These are what we are looking for. EI, and the length is given. Our length is 5 for the first element. Fill in everything we have. Is the same thing that we calculated earlier for K1, so the same values. Here V1 and V2, since element 1 is bordered by node 1 and 2, these are 0. Our slope for at point 1 and point 2, we calculated right here, minus this one. Now, this one, again, we're gonna use the formulas that we had right here, and we're gonna calculate based on these exact same ones. So, whatever values we have here, we're gonna calculate them and plug them in right here. The negative 15, negative 1250, 15,000, and 12,500. The equivalent nodal forces on element 1. We know everything on this side. These are the only unknowns. Multiply everything out, subtract these, and we are able to find our elemental forces and moment for element 1. For element 2, we follow the exact steps that we did for element 1. Just pay attention that everything that you are working with is for element 2. F2y and F3y, since these are the two nodes that are bordering element 2, M2, M3, belonging to element 2. Fill in everything that we know. Our elemental equivalent nodal forces right here from the same formulas, just like we did for up here, and we can find our values right here. Now let's go ahead and find our global reactions, the F1y, F2y, F3y. If we look close for element 1 at node 1, all we have is F1y as a reaction. There's no other global force, and only elemental force is F1y for element 1. These two are equal. F1y global force is equal to 11,850. Now, the same situation is happening here for F3y, where we can equal it, put it equal to F elemental 3y, which belongs to element 2. We have 8,060 newtons. Now for element 2, reaction F2y, we have this node is shared by both elements, element 1, element 2. Therefore, when we calculate global force 2y, we need to add these two up. The local force from element 1 plus the local force from element 2. These two added up, here's our value. Now for our global moments M1 and M3, the same process. We can put it straight equal to our elemental M1, this one elemental M3, which is both are 0, which should be logical for us because this is a pin and these are rollers. 1 and 3, we can see that there's should be a 0, right? There's nothing holding this back from pivoting around those points. Now, M2, also a roller support, so we should not have any moment reaction as well. So here, when we calculate it, we can see with numbers that global moment M2 equals the M1, M2, little m2, belonging to element 1 plus the little m2 from element 2, these two, when we add it up in the sketch, this is how they would act. This plus this, we can see that also gives us 0, which is correct because it's a roller support. There's no moment reaction at either, or I should say neither of the three.